set building. In all of these previous examples, these are sort of things. I'm talking about things which you could say are natural in the world. I'm talking about Mean Girls. And, most of us have grown up and we've met Mean Girls, and god damn, are they mean. But I can use these examples as intuitive because we have some sense of groups of people. When I move on to set building, I'm now really diving into the abstract mathematical realm, because these are the operations that allow us to do math in some very fundamental sense. That in mathematics, we start out, sets are Lego blocks to build everything else. And these are all the rules that tell you how you can connect Lego blocks to make different operations. Like, how do you go from sets to algebras, to topological spaces, to function spaces, to limits, to calculus, to real numbers? How do you do that? What gives you the power to do that? And the operations that give you the power to do that are these operations. And so a lot of these operations, it makes less sense to talk about the Mean Girls, and so unfortunately we're going to have different examples. We're going to have examples that are more abstract and mathematical, so with a heavy heart, I'm going to have to say goodbye to the Mean Girls. Ugh, it hurts, it really does. So we're going to start with the set product, A \, times B. This is simple. It's if you want to write it symbolically, it's just it's just the standard product symbol that we use everywhere. But if you do \, times, there's something Cartesian about it. And this is all the sets of pairs of elements. Let's make this smaller. Again, you can see how I'm using with A and B. Where exactly, if I have an element in A and an element B, I'm going to get a unique pair in A comma B. And so, for example, if these are two finite sets, like these, A is the set of first names I'm considering for a baby, and maybe B is the set of middle names I'm considering. So I have 10 first names and I have 3 middle names. A times B will be the set of prefix names for your baby, just assuming you've decided on some last name hereditarily. Then you'd get 30 elements for pairs of first names and second names. So I guess that's kind of a natural example. But another way is you could start with something like the real numbers, math BBR. Why is this mad at me? The real numbers, which you represent by some number line like this. And maybe you want more dimensions, and so you take the product of the real numbers with itself, the Cartesian product. This is where it really gets its name. And this gives you the plane, gives you the real plane. Let's get this out of the way and zoom down here. That gives you another axis. It gives you another axis. And you can keep going. You can say, okay, maybe I want more than 2 dimensions. I want an object with 3 dimensions. See how we're building an object that's getting kind of bigger and bigger? We're set building. We're doing set building operations. And I add a 3rd dimension, which, I'm not great at drawing, but let's see if the perspective gets there. How does that look? Does that look 3D to you guys? You let me know. Looks a little short in the front, but that's fine. And so on and so forth to make higher and higher dimension stuff. Now, the next example, if I want to add another one, it's kind of hard to visualize what that looks like, but it's something that we can represent with symbols and mathematically. And this is set products. And this is kind of a pain to write down. So at this point, we start writing stuff like this. We do math RB to the 4th. So we do the power of a set to the 4th, which just means taking the product of a set with itself 4 times. Maybe technically it's slightly different, but it's not different in a way that matters. And then, you're doing calculus, multivariable calculus, or abstract linear algebra, and now you're working with these arbitrary spaces of dimension n by taking products with itself. And so another example of a product is this a to the n. We have yet another example of a product symbol, is that sometimes we like to take really, really big products. So for example, maybe I want to define this thing r omega. And this guy is a big object. And we might write this as prod I equals 0 to inf d of BBR. So let's look at this equation that I wrote down here. We're going to do big prod. Is that not a thing? Okay, it's not a thing. So let's do a display mode so it looks better. Sorry, I keep stalling on you guys. All right, that looks better. So what's going on with this? We have, essentially, this is another example of a product symbol. We have 3 symbols in here that all represent product, but set products are really important. That this one allows you to do products, a set with itself finitely many times. This one allows you to do individual products, product of 2 things. This one allows you to be very general, and it's often used for infinite products. And so we can define r to the omega, which is an infinite product. So this is an infinite dimensional R vector space. And in fact, it's actually bigger, and it's a different object than maybe you've seen this, r to the inf d. These are 2 different things. In a real sense, these are actually, if you know linear algebra, these 2 spaces, r omega and r infinity, are dual spaces to each other under as linear duals. So in some sense, they're mirror images, but they're not equal, or they're not isomorphic. For finite dimensional spaces, they're all isomorphic. But the product also allows you to do stuff like, you could do, what's a good product of sets? Oftentimes you'll have some construction where you're doing some big product of like over some index alpha of u alpha, where each of these u alphas are different. So it just gives you notation to allow you to express your products even if they're infinite, where these elements may vary. And so products allow you to build up so many big sets and big examples. I'd love to talk more about them, but there's so many important examples. So we're going to move on to set exponentiation and power sets. And we're putting them in the same section because, frankly, they're kind of similar. These are similar operations. So P of A is exactly the subsets of a set A. So it's usually written mathcal P of A. And it's exactly, using this notation again, it's the sets, we'll call them S. Move this down here. S. Give me a second. Mid. Just such that S is a subset of A. Why is this mad at me again? All right. It seems like not the biggest deal. When is this used? Well, it allows you to make bigger infinities. Famously, this is something we're going to prove in this series. If A is infinite, then mathcal P of A is bigger than A in terms of cardinality. That you'll get a bigger infinity if you take the power set of an infinite set. And once you prove this, you prove that there are infinitely many infinities because you can just keep on taking more and more power sets. In practical terms, where is this used? Well, you might use this to define the topology on a set. A lot of things are structures on subsets of sets. And so it's useful to have something this powerful. But oftentimes, like axiomatically, we have this to allow us to make very big sets, essentially. Like this allows us to show that there are infinitely many infinities by using this theorem, which we'll show later. Now, what is this? This is something similar to power set, like I said. B to the A is set exponentiation is equal to it's equal to precisely functions from I always get this wrong. Is it A to B? Yeah, it is A to B. You think about it for a second and you get there. Yeah, it's all functions A to B. So that's good to have. So there's no mid. It's actually just all functions from A to B. And so what's a construction you can do with this? Well, let's suppose that I take the natural numbers to the power of the real numbers. Seems curious of what this would be. Oh, I got this wrong. This is definitely not what I want. That's a very different object from what I want. I'm moving it around instead of... I want the other power. Much better. This is precisely functions from the natural numbers to the real numbers. And what are functions from the natural numbers to the real numbers? Those are sequences in the real numbers. And so now we can talk about if we're in the real numbers, we can have, sequences of points, and then you can take the subset of this. You can use this set, which is sequences of real numbers, and you can take a subset of it of which ones converge using the set comprehension operation we talked about earlier. We can say the subset of this which converge, and then you can talk about different subsets. Maybe you want this subset which converge to a point between 0 and 1. It allows you to talk about all these general objects. And a thing to notice is that r to the n is equal. I'm going to write this sort of slimy type of equals, which means isomorphic or equivalent, to something we talked about earlier, which is r to the omega. All of this sort of symbology fits in together well. Like, you might be asking, why the hell is exponentiation of sets the set of functions from A to B? Like, why does that make sense? Well, a fun fact is that if B and A are finite sets, the size of the exponential from B to A is exactly B to the power of A. Now, why is that? Well, basically, the reason's pretty simple, is because for each element of A, you have to pick an element of B. So how many choices do you have for the first element of A? Well, you think about it, you have B choices. How many choices do you have for the second element of A? Well, you have B choices. How many for the third? You have B choices, and you multiply B by itself A many times, and you'll get the size of the exponential. Other properties work out too. Like you'll get B to the A1 times A2 is naturally isomorphic, which means isomorphic but in a good way, to B to the A1 to the A2. So this property, which you'll recognize from exponential functions, works for exponentials of sets. And in a sense, this is the real exponential product relation that when we're talking about numbers, the numbers inherit it from this structure rather than the other way around. Is that we don't generalize this thing from numbers. Numbers are sort of an example of this thing from sets. And I would say you should try to think about or prove this on your own. It's doable. But it's subtle, because the subtle thing is making sense of this object. Because this object is a little confusing because it's functions from a set of functions to a set. This object's a little confusing, but if you look up currying or you find a Haskell programmer, they'd love to explain it to you because those people are just looking for something to do. All right, we're getting down to it. These two operations are not very similar. Oh, I forgot to tell you why the power set is similar to exponential. And the reason is that another natural isomorphism, mathcal PA, is sometimes written like this, as 2 to the a, because we can consider the functions from a to a set with 2 points, where if you go to one point, it means you're in the subset, and if you go to the other, it means you're out of the subset. But right, rushing on along, we gotta talk about these two guys, which are both important, and there's so much to say about set building, because so much of mathematics is just set building. It's just building, it's just using your sets to make an object that you want to work with, and making sure that all the properties work out. And so it's really a big deal. So this is disjoint union, and this is a weird one. And so basically, it's like a union of two sets, but if those sets have an intersection, you say, no, they don't. You pretend they don't. And so, for example, if I were to do, we're using the real numbers law. If I do the union of R with itself, what do I get? Well, I get the real numbers back. Because if you take the union of any set with itself, you get the real numbers back. But what if I take instead the disjoint union? And then coprod is the symbol. What does this look like? Well, even though these guys have a sizable intersection, we're treating them like they are disjoint. And there's a lot of different ways to do this. There's a lot of different technical ways to do it. But the best way to think about it is that like you're making a copy. So you start with your real number line. Here it is. And then if I want to form R disjoint union R, all I do is I add another one. Here you go. And I consider the set of both of these. And so R disjoint union R is like having 2 lines. And great news. And similarly with products and coproducts, you can keep doing disjoint unions. You can do something like this, coprod underscore I equals 1 to infinity of math BBR. You can do something like this. And this would give you countably many R's. So you would have just a lot of lines like this going on and on and on, all disjoint, all non-intersecting. And I was trying to think of a good example of disjoint union for you guys. And the way we use disjoint union is we use disjoint union all the time in topology. So all the time in topology, we want to make a set. And the way we make a set is we kind of do cut and paste. Like we start off with like a few objects. We start off with maybe some little points, like a few points. Imagine those are points instead of lines. And we start out with a few lines. And then we start gluing them together. And maybe we start out with, maybe we have a few disks as well. And then we start gluing them together. We start saying, hey, we attach this point here, and then we attach some point here, and we start making spaces by first taking disjoint unions of all of our building blocks, and then gluing them together. And how do you glue things together? Well, the way we glue things together is with our last operation, which is the most subtle one. Well, it depends on your perspective. I would think of it as the most subtle one, but this is called set quotient, or modding out by an equivalence relation. And this, it takes some work to define this one. So for example, you have to say what the hell is going on with this tilde because the tilde changes. So you have to define a thing called an equivalence relation. So we're going to, on a set. So we're going to first define that. An equivalence relation is something that's like equals. I don't know why it's unhappy. Okay, there it goes. So what's an equivalence relation? Well, it's a function from a set, from pairs of a set to true comma false. Let's make this smaller so that you can see it. And what are the properties of this function? Well, it has a bunch of important properties. One is that for every A is equivalent to A. So this is how we write the function, among other things, is that we write it by the symbol. And when we write A tilde A, it means that the function on A times A is true rather than false. So it's a relation. The functions from A times A to true comma false is another word for a relation. And they have all of these things that are similar to equality. It's kind of like a weaker form of equality that we are asking for. So for all A that is similar to B is similar to A, this kind of reflexive property, and then the transitive property for all A sim B sim C, then A is similar to C. So that's an equivalence relation. What's an example of an equivalence relation? I gave an example going back to my notes that I have up there, is that if I have a set of people, you could say any kind of biometric of them. So you could say the BMI of a bunch of people is an equivalence relation. Like one person is equivalent to another person if they have the same BMI. Or you could say height. Or you could say eye color, if you can define eye color in a well-defined way. That, if two people have the same eye color, we all know all people with blue eyes are kind of the same. There's some sort of shared equivalence to all of them when they look at you with their weird piercing blue eyes. And so lots of things like that are equivalence relations. But one of the key places we use equivalence relations is going back here. And so let's just make a space. I've been doing a lot of talking, but I'm going to show you one way to make a torus that is actually done in mathematics. So in mathematics, what do we need for a torus? Well, a torus is actually a two-dimensional space. It's shaped like a donut. It's actually shaped like the surface of a donut. A lot of people get confused with that. They think it's sort of a solid donut. It's actually all hollow. If you bite into that torus, you're not going to get much, unfortunately. So here's one way that in mathematics we construct a torus. We start with a single point. Like this is something you'll do in topology classes. Start with a single point. Then you'll add in two line segments. And so to add in two line segments, you're actually you're using the disjoint union. Like we'll call these line segments I, and so you disjoint union with these two line segments. And then we add in one solid disk. A solid disk, which I'm drawing here. And you might be looking at this and thinking, how the hell are we going to get a torus out of this? Well, this is where we use the power of modding out by a set. So I've told you what an equivalence relation is, but I haven't told you what modding out by a set is, because I want to show you. So we're going to define an equivalence relation on this disjoint union of points. So what does this disjoint union look like? We have a single point, we have two line segments, and we have this we have this thing right here, this whole disk. So I'm going to define this equivalence relation manually. First, to define we know every point is equivalent to itself, but I'm also going to say, is there a way I can do dashed lines? You can figure that out. I'm going to say this endpoint of this line segment is equivalent to this point. And I'm going to say this endpoint is equivalent to this point. And I'm going to say this one's equivalent to this point. And I'm going to say this one's equivalent to this point. And so what does this do? Well, this is exactly what I mean by gluing. That if I say these are all equivalent, let's say I want to visualize these things where I treat equivalent points as equal. Well, then what do I get? I'm going to draw the central point in pretty pink because I don't know, I like pink. And then I'm going to draw my two line segments just to keep it different in blue. Now, if the ends of the line segment are equivalent here, I end up bending them and I get this arc. And then if I do it for the other line segment, I get another arc and I get this little figure eight. This kind of figure eight thing. I'm going to have to think to myself for a little bit. If I go around, I want to go around one way around the figure eight. I'm visualizing a torus. We're making the skeleton of a torus. So we start with, you look in the corner of the screen, we start with this figure eight, and to visualize it, we twist part of it. Now this hole is going to become the hole in the donut, and this hole is going to become part of the donut proper. And the last thing we're going to do is you can glue the disc onto this in such a way, one gluing of the boundary of the disc, such that you get a torus. And I'm fearful that I'm going to get this gluing wrong. Like you want to glue one way around this way, then one way around this way, then one way around the opposite way, and then one way going all the way back. So you get... Is that right? I'm going to assume that's right. But maybe I'll leave a top comment to this video of how you actually define a torus. So this is going to be quite confusing. I'm going to do another color because there's a lot going on. Now we're going to do the green disc, green boundary disc. We're going to have the inside be light green. And here's how we're going to do the rest of the equivalences. We're going to say for the first quarter, this first quarter of the boundary of the disc, we're going to glue it one way around this loop. So we're going to have it go around this loop once. The next quarter, we're going to have it go around this loop once. And then the next quarter, oops, that's a little too much. The next quarter of the boundary, we're going to have it go around this loop again, but the opposite direction. And then the last corner, we're going to have it go around this loop again, but the opposite direction. And this is hard to do. You could try to do this with a paper disc. But if you were to glue all these points together to that figure eight, you would get something which is topologically a torus. This is how you glue the two-dimensional sheet onto this one-dimensional boundary to get a torus. So what this is modding out by an equivalence relation. So now I'm going to define what modding out by an equivalence relation means. In this case, the set A was equal to a point, which we'll write as ast, two line segments, which we'll write as I because those are intervals, and a disk, which we'll write as D2, which is how a disk is written. So we start with this set, this disjoint union, which was our point, our I, and D2. And then we defined an equivalence relation sort of little by gluing. We say we're going to make this equivalent to this equivalent to this equivalent to this, etc., which is gluing data. And the set A mod tilde is exactly the torus, is the set you get where you treat all of the elements which were previously equivalent as being equal. And so maybe a simpler example, oh, I should have done a sphere. Let's do a sphere right now. That's way easier. Let's do another construction. Sphere. Way easier. I don't know why I did a torus. That's, well, there's easier constructions of the torus. So a sphere is easier. Our set is just going to be a single point and a disk. So very easy to work with. So we start out with our set A. And our set A in this case is going to be a point. So set with one element. Disjoint union, coprod, a disk. Okay. Now what's the equivalence relation? If I have a point and a disk, how do I make a sphere? Well, it's actually pretty simple. If you were to picture my hand as this sort of disk, and I have one point, I'm just going to make every single boundary point, I'm going to collapse it to that one point. It's sort of like, again, if you glue all the parts of a circle to one point, every single point on this boundary is going to be equivalent to this point. You get a sphere. Because it's kind of like, it's almost easier to picture in the opposite. That if you poke a hole in a balloon and stretch it out, you'll get a disk. But these are really the intuitive things that you do in topology. And so you define this gluing data as follows. And then your A mod sim is equal to a sphere, a two-sphere, which we write this way. Man, this video is getting long. I don't know. Maybe I'm going to make this multiple parts. Because I'm really going here. But last thing I'll do is I'll make sure to define formally what A mod sim means. So formally, this is the set of equivalence classes, which we write like this. For X in A. An equivalence class is, if we write this relative to some relation, is a subset of A. Oops, I keep writing backslash. Which is exactly the set of all points which are equivalent to X. So for example, in this example, where I have the data defining a sphere, oh, this wants me to eat something. Where I have the data defining a sphere, the equivalence class of this point is exactly the point and all the elements of the boundary of the disk that we're gluing to the point. And then the rest of the equivalence classes are all the individual points inside the disk, which just becomes points on the sphere. And so when we take modulo an equivalence class, we are really collapsing things by equivalence. And while formally they're given by these equivalence classes, a better way to think of them is precisely as you change the sim relation into an equality relation. Like you force things to be equal. Where previously this point was not equal to all these boundary points, now they are. And that enforces that all the boundary points are equivalent to each other as well. In this complicated torus example, similar stuff happens, but it takes a little while. So you can see there's a lot going on with, I was going to do this example, but I think I have enough examples. There's a lot going on with set building. But the process of set building is really two steps. It's really most of these set building operations. I'll actually go back to the first page. Almost all of these operations they're kind of like you start with some clay and you're putting lumps of clay together. You're making bigger and bigger sets. You're taking products, you're taking disjoint unions, you're adding clay. And then you use, in most cases, these two operations to sculpt, to cut away from the clay. Like you'll use this to define sequences, and then you'll sculpt away and get convergent sequences using this. Or you'll use this to give you a bunch of pieces of spaces, and you'll use this to glue pieces of those spaces together to give you spheres or tori, or all these things you use in topology. But the process of set building is using these powerful operations to make your sets, to make something big enough to be the object that you want, and then using these two operations to sculpt clay away to get precisely what you want. You don't want something that's just big, you want something that's big but also useful. You also use these operations in your sculpting process as well, in practice. But, this has been way too long of a video. And so if you really want, like, if literally 5 people comment that they want me to do this example, making the integers from the natural numbers by scoreboard construction, run differential construction, I'll do that. But I think I've talked a lot here. And the overall theme of set building is that you make big sets here out of clay, and then you sculpt away and make them precise using these tools.